There is a belief, held quietly but deeply by the people who live on the islands of the Western Pacific, that the Mariana Trench protects them. It makes a certain intuitive sense. The trench is there, vast, ancient, the deepest place on Earth, sitting between their islands and the open Pacific like a geological guardian. Surely something so enormous, so profound, so fundamentally different from everything around it must serve some protective purpose. Noé has a different answer. The Mariana Trench does not protect the islands above it from tsunamis. The Mariana Trench is the reason the islands above it are in danger. Not because of what it is, because of what it does. Because of the geological process that created it and continues to drive it, slowly, invisibly, with a patience that makes human civilization look like a weekend. Subduction. The Pacific Plate, one of the largest tectonic plates on Earth, covering nearly a third of the planet's surface, is moving. It has always been moving. It moves at roughly the speed your fingernails grow, but it has been moving for 180 million years. And in that time, its leading edge has pushed up against the Mariana Plate and begun to slide beneath it. Not gently, not smoothly. In fits and starts, locked and releasing, accumulating stress over decades and centuries, and releasing it in moments that we call earthquakes. The Mariana Trench is not a guardian, it is a wound. A scar in the ocean floor where two plates are locked in a slow, violent argument that has been running since before the dinosaurs went extinct. And in approximately 50 years of modern seismological monitoring, we have never recorded a truly large earthquake here. The silence is not reassuring. The silence is the question. What if the Mariana Trench finally breaks? To understand why the silence is terrifying, you need to understand how subduction zones work. When one tectonic plate slides beneath another, it does not slide smoothly. The two plates are rough, covered in geological irregularities, seamounts, ridges, and variations in density and composition that cause them to lock together at certain points along their boundary. These locked zones are called asperities. They are the friction points where the stress accumulates. As the plate continues to move 1 centimeter, 2 centimeters per year, the stress at the asperity builds. The rock does not bend, it compresses. It stores the energy of the moving plate the way a spring stores the energy of compression, invisibly, patiently, without any external sign that anything is building, until the asperity fails. When it fails, the stored energy releases in seconds. The seafloor lurches, meters, sometimes tens of meters, in a single violent movement. The water column above it is displaced simultaneously. A tsunami is born. The 2004 Indian Ocean earthquake, magnitude 9.1, generated a tsunami that killed 227,000 people across 14 countries. The seafloor moved 20 meters in the time it takes to blink. The 2011 Tohoku earthquake, magnitude 9.0, generated a tsunami that killed 19,000 people in Japan and triggered the Fukushima nuclear disaster. The seafloor moved up to 50 meters. Both of these earthquakes occurred in subduction zones that seismologists had previously assessed as unlikely to generate events of that magnitude. Both assessments were wrong. The Mariana Subduction System is one of the longest subduction zones in the world. It has generated moderate earthquakes, magnitude 6, magnitude 7, but in 50 years of modern monitoring, it has not generated a magnitude 8 or above. There are two explanations for this silence. The first, the locked zone in the Mariana Subduction System is structured in a way that prevents stress from accumulating at the scale needed for a large earthquake. The geology is different. The plates slide more freely. The silence is genuine safety. The second, the locked zone is accumulating stress in a pattern that has not yet reached its release threshold. The silence is not safety. It is waiting. After 2004 and 2011, the scientific community no longer dismisses the second explanation. You have been in the habitat for 11 days. This is your third HADAL mission. After the year in the Challenger Deep and the 40 days monitoring the methane cascade. The habitat is familiar now in the way that an uncomfortable truth becomes familiar. You know its dimensions, its sounds, its routines. You do not love it. You have accepted it. The mission this time is geological. Your habitat is positioned at 7,800 meters depth on the inner wall of the Mariana Trench, not at the bottom, but on the slope. Your instruments include a broadband seismometer, a tilt meter, a bottom pressure recorder, and a hydrophone array that can detect sound across hundreds of kilometers of ocean. You are, in the most literal sense, an ear pressed against the wall of the most seismically significant geological boundary in the Pacific Ocean. Outside your quartz window, the familiar dark, the marine snow, the slow drift of bioluminescent organisms in the mid-distance. But underneath all of it, underneath the biological quiet, underneath the geological stillness, your seismometer is always listening. It has been recording a sequence of very small earthquakes for the past 4 days. Not unusual. Small earthquakes are constant along subduction zones. Your instruments record dozens per day. They are background noise, the geological equivalent of a building settling. But the sequence from the past 4 days is different in one specific way. The events are migrating. Each small earthquake is occurring slightly closer to a locked patch of the subduction interface that your instruments have been mapping since the mission began. A locked patch that, based on the GPS data from surface stations and the deformation pattern your tilt meter is recording, has not released stress in a very long time. You have been running the analysis for 6 hours. The results keep coming back the same. You pick up the communication handset and begin transmitting to the surface support vessel. The geology beneath you is more complex than any textbook diagram suggests. The subducting Pacific plate is not a flat sheet. It is a dynamic, three-dimensional structure, bent by the forces acting on it, scarred by 180 million years of geological history, carrying on its surface a collection of seamounts and ridges and chemical variations that interact with the overriding Mariana Plate in ways that are still not fully understood. At depths between 10 and 40 kilometers below the seafloor, below even the bottom of the trench, the two plates are in contact along the subduction interface. Most of this interface is aseismic. The plates slide past each other too slowly and too smoothly to generate significant earthquakes. But at certain patches, the asperities, the plates are locked. The locked patch your instruments have been mapping sits at approximately 15 kilometers depth below the seafloor of the inner trench wall. It is roughly 80 kilometers long and 40 kilometers wide. Based on the GPS deformation data from surface stations on Guam and Saipan, it has been accumulating strain for at least 30 years without releasing it. 30 years of accumulation. At the convergence rate of the Pacific Plate, approximately 6 centimeters per year, that means approximately 1.8 meters of stored displacement. When the locked patch fails, the seafloor above it will move by at least that distance, possibly more if the failure cascades to adjacent sections of the interface. A seafloor displacement of 2 meters across an 80 by 40 kilometer patch of the Mariana Subduction zone will generate a tsunami. The Pacific Tsunami Warning Center will receive the seismic signal approximately 2 minutes after the earthquake begins. It will take 15 to 21 minutes to analyze the data, model the tsunami, and issue a warning to coastal communities. The fastest tsunami propagation from the epicenter to the coast of Guam, 200 kilometers away, takes approximately 10 to 45 minutes, depending on the depth of the rupture and the directional focusing of the wave energy. In certain scenarios, the warning arrives after the wave. You are transmitting this analysis to the surface when the seismometer alarm activates. The initial P wave arrives at your seismometer at 14:32:07 local time. P waves are compression waves. They travel faster than the S waves and surface waves that carry most of the destructive energy of an earthquake. They arrive first. They give seismometers the first warning. They feel, at moderate distances, like a brief, sharp jolt. A knock on the door before the door is broken down. Your seismometer records the P wave arrival. The amplitude is larger than any event you have recorded in 11 days. Your instrument calculates a preliminary magnitude, 7.8. 7.8. Large. Significant. But the preliminary magnitude from a single instrument is unreliable. It takes a network of seismometers spread across hundreds of kilometers to accurately calculate the magnitude and location of a major earthquake. You have one seismometer at the epicenter. The S wave arrives 43 seconds later. The habitat moves. Not catastrophically, not the structural failure you have rehearsed in your emergency protocols, but it moves. A lateral displacement, the habitat shifting on its anchor points as the seafloor beneath it lurches. The quartz window flexes slightly. The instrument racks rattle. A coffee cup slides off the edge of the monitoring station and falls to the floor in the low-gravity feeling slow motion of a sealed, pressurized environment. Then the surface waves arrive, and the magnitude estimate updates. 8.7. You look at the number for a moment, then you look at the hydrophone display. The tsunami signal is already propagating through the water column above you, not as a surface wave, not yet, as a pressure pulse, moving outward from the epicenter at the speed of sound in water, carrying the energy of a seafloor that just moved 2 meters in 43 seconds. At the surface, 7,800 meters above you, The ocean has just risen. You cannot see the surface. You cannot see Guam. You cannot see the 160,000 people who live on an island 200 kilometers from where the seafloor just moved. But your instruments can tell you what is happening above you, and the picture they paint requires no imagination to be terrifying. The tsunami generated by an 8.7 magnitude earthquake on the Mariana Subduction zone is not a wall of water. That is not how tsunamis work. At sea, it is barely noticeable. A long, low swell, perhaps a meter high, passing at the speed of a commercial aircraft. Ships at sea do not feel it. But as the wave approaches the shallow waters around Guam, something changes. The ocean floor rises toward the surface. The wave, which has been traveling through deep water, with its energy spread across the full depth of the ocean column, suddenly has nowhere to go but up. The wave slows. The energy compresses. The height increases. By the time it reaches the reef shelf around Guam, it is no longer a meter high. The models, run by the Pacific Tsunami Warning Center in the minutes after receiving the seismic signal, show arrival times between 18 and 32 minutes from the moment of rupture, depending on the direction and coastal geometry. The warning is issued at 14:49:03, 16 minutes and 56 seconds after the earthquake began. The first wave makes landfall at 15:09:41, 37 minutes and 34 seconds after the earthquake began. The people of Guam had 20 minutes and 38 seconds between the warning and the first wave. Whether 20 minutes is enough depends on where you are when the warning arrives, whether you have practiced the evacuation route, whether you recognize the natural warning sign, the rapid withdrawal of the sea from the shoreline in time to run for high ground before the withdrawal reverses. FEMA's models suggest that if the population responds 5 minutes slower than the optimal evacuation scenario, the casualty count increases by a factor of more than 1,000. 5 minutes. The difference between a geological event and a human catastrophe is 5 minutes of decision-making by people who are already afraid. You are the only human being at the epicenter of an 8.7 magnitude earthquake. Your habitat is intact, the engineering held, the anchor points held, the pressure seals held. You are alive at 7,800 meters depth, listening to the hydrophone data as the tsunami propagates outward in all directions above you. The aftershocks begin within minutes, magnitude 6.1, then 5.8. Then a sequence of smaller events as the stress redistributes along adjacent sections of the fault. Each one registers on your seismometer. Each one is another data point in the most important geological data set ever collected from inside a major subduction zone rupture. You are doing science in the middle of the thing you came to study. The instruments are running. The data is transmitting intermittently through the acoustic modem that connects you to the surface support vessel, which has been moved to deep water as a precaution against the tsunami. Outside your quartz window, the Mariana Trench looks exactly as it did before. The marine snow drifts. The bioluminescent organisms pulse in the mid-distance. The gray silt of the inner trench wall is unchanged. The earthquake that just killed, that may have just killed, people on the surface above you left no visible trace in the world you can see. The seafloor moved. The water column moved. the energy propagated. But the darkness outside your window is the same darkness it was before. The trench does not know what it has done. It never does. It will do it again. Not in your lifetime, probably. The stress on the locked patch has been released. The asperity has failed and reset. It will take decades, perhaps a century, to accumulate enough strain for the next major event. But it will accumulate. It always does. You sit in the habitat at 7,800 meters depth, listening to the aftershocks on your seismometer, and you think about what the people above you are doing right now. Whether the warning came in time, whether 20 minutes was enough. And you think about the islands that sit above other subduction zones, zones that have also been silent for 50 years, for 100 years, for longer than modern seismology has existed to listen. Silence is not safety. Silence is the question that has not yet been answered. The answer, when it comes fast. What if the Mariana Trench finally breaks? The science says it can. The history says it will. The only question is whether the warning arrives before the wave. What should HADAL explore next? Should we descend into the hydrothermal vents of the mid-Atlantic ridge, where water reaches 400 degrees Celsius and entire ecosystems thrive in conditions that should be chemically impossible? Or should we witness the slow disappearance of the Great Barrier Reef, the largest living structure on Earth, bleaching and dying in real time, 1 degree at a time? Vote in the comments below and subscribe to HADAL before the ground moves.